Beautiful blue sky day today here in Brisbane, Queensland, Australia. And it made me think that we're pretty lucky that we get just about the right amount of rain, not too little and not too much. And worldwide, life on Earth depends on just the right amount of rain. And it turns out that depends on a bit of physics, which also lets you predict how high the clouds are. Have you ever wondered what makes the clouds sometimes sort of puff out there and sometimes go all the way to what appears to be the top of the sky? Well, that's what this video is about. Okay, so first of all, of course, the rain falls from the sky, but it comes from the ground, and moist ground or the ocean. So it's lifted from the ground up into the sky. And how does that happen? Well, we're familiar with things floating. So a piece of wood floating on water or a ship floating on water. Effectively, the reason it floats is because it has what's called buoyancy. In other words, it's lighter than the water it displaces. And so the rest of the water around it just buoys it up. So if something is lighter or, shall we say, less dense than water, then it will float on water. And it's the same in air. A hot air balloon is on average less dense than the air around it, so it buoys up. Okay, so if you've got the sun coming down onto the ground and heating the ground, then the air that's just touching the ground, maybe in the first few hundred feet, 100 meters or so, is going to be warmed by its contact with the ground. And it will eventually gain some buoyancy because as it warms, it becomes less dense and it will start to bubble up from the ground through the atmosphere. As that bubble of air rises through the atmosphere, it carries whatever moisture it had at the ground level. And if the ground was very dry, then not much moisture. If the ground was very moist, such as greenery or crops, or if it in fact wasn't ground, if it was the ocean or a lake, then it would be carrying more moisture. Now, also we know that as we rise up in the atmosphere from ground level, higher and higher in the atmosphere, the pressure gets less because there's less atmosphere above to provide that pressure. So pressure decreases with altitude. Generally also, the temperature will decrease with altitude as well. So it's obviously warmer here on the ground than it is at, say, 5,000 feet in the air. But that's the key. Just how rapidly the temperature falls as we climb through the atmosphere is actually the key to whether it rains or not. Okay, so going back to our bubble of air. If that bubble of air, let's imagine that bubble of air was being lifted by the heat of the ground, which ultimately is the heat from the sun, and it gains quite a bit of temperature differential as it's heated, so it's going to bubble up a little bit, it's going to gain some momentum, and it'll bubble up through the atmosphere. And if it has enough momentum and speed, it might reach a height where, as the temperature falls, it can no longer carry the moisture that it had at ground level. And if it's lifted up past what we call the condensation level, then that moisture condenses out into cloud. And if there's enough of it, that cloud could precipitate rainfall. Now, in mountainous areas, when there's a wind blowing up over a mountain, sometimes the wind is actually lifting the air. And so on the upwind side of a mountain, you might get to a point where that air is raised above its condensation level, and so fog initially forms, fog, cloud, and maybe rain. So you'll get a wet side of the mountain on the upwind side, and that air as it goes over the top of the mountain is dry. So on the other side, it's actually dry. And you see that in areas where there's a mountain range, like the Great Divide in Australia. To the west, it's really dry, and to the east, it's moist and wet. And you also see it in North America, the Colorados. You see it in South America, the Andes Mountains, and throughout Europe as well. But in this video, I'm not talking about when wind and a mountain or terrain is lifting cloud. No, I'm talking about a bubble of air being heated from the ground by the sun. So in general, if that bubble of air is warmer than the air around it, then it will be also less dense and therefore more buoyant, and it will continue to rise. In fact, it will accelerate if there's buoyancy. And if it gets to the point where, as the bubble of air cools, as it rises, it becomes the same temperature as the surrounding air, then it will no longer accelerate. It might continue at some speed for a little while, but eventually it will basically come to a stop because of friction. So at that point it becomes neutrally buoyant, no buoyancy. So it's travelled from the ground because it was initially warmed by the ground, which was warmed by the sun, and it's zoomed up to some height, and then it reaches an altitude where it's no longer buoyant, and that's where it stops. And it might even cool further and come back down again to the ground. Okay, but if it's lifted sufficiently high by its initial momentum, for example, to reach a point where it can no longer carry that moisture, then cloud will form. But that's not necessarily rain, because we often see clouds in the sky, and yet they don't necessarily all produce rain. Right, so the cool thing is that at some point, if that parcel of air has reached its saturation point, so cloud starts to form, at that point, the rate at which it cools as it rises changes slightly. So as the bubble of air rises up from the ground, it's cooled because it's expanding, the pressure is reducing, so it's expanding, so it'll be cooling. But it may not be cooling as fast as the outside air temperature or the ambient air temperature. So it may still be warmer than the ambient air temperature. And if it's warmer at any point in its ascent, it's going to keep going up. And if it gets to that point where cloud starts to form, then the rate of change of this temperature of this bubble of air is going to alter a little bit. In fact, a bubble of air that has cloud, in other words, it's 100% saturated, if that continues to rise, then it will cool at slightly different, less rate. In other words, it will cool less quickly than if it were dry. So it's cooling, and then it's still cooling above where the cloud forms, but it's not cooling as fast. In other words, if the outside or the ambient air temperature is kind of constantly going down in temperature with altitude, and this bubble of air has got to this height and still is buoyant, then as it releases more moisture into itself, more water vapor condenses, then actually that temperature differential becomes more pronounced. It actually is warmer than the outside air or the surrounding air, even more. And as it rises, even more. So it will actually get increasingly buoyant. It will accelerate. So once that moisture starts to form, this bubble of air gets a kick on and it accelerates further up. Now the interesting thing about this is that most of the time that doesn't happen. Most of the time the surrounding air is cooling more slowly than the bubble of air rising up, whether it's dry or whether it's saturated. Most of the time, a bubble of air going up will eventually stop at a point where it's no longer positively buoyant. But sometimes, and this is the key, sometimes the ambient air temperature is kind of between those two rates at which the bubble of air cools, whether it's dry or whether it's saturated. So it might be that if a bubble of air reaches its saturation point, the condensation level we call it, it suddenly starts to accelerate because the outside air temperature or the ambient air temperature is cooling more rapidly than the parcel of air going up. In other words, the parcel of air going up is relatively getting warmer and warmer with altitude. And so of course it's going to accelerate. And it's going to accelerate until those conditions are no longer the case. Now what happens is that does happen at a particular height. So what we said before about generally the air temperature decreasing with altitude is true up to a certain point, and that's at the top of our what's called the troposphere. And above that, the temperature actually starts to increase again. So if this bubble of air was accelerating, it would hit a point where where the outside air temperature was suddenly warmer than the parcel of air, and then it would become negatively buoyant again. So it's basically going to accelerate up to a point where it's no longer buoyant. What altitude is that? Well, under normal conditions, the altitude would be the top of the troposphere, which is somewhere between 30,000 feet, 40,000 feet, 50,000 feet. And that represents the point in the atmosphere above which most of our weather is below. So that's why airlines, for example, cruise at that altitude. They want to be above the weather, above the turbulence, above the storms, so to speak. And that's also why thunderstorms, which are in fact caused by this accelerating bubbles of air going up, carrying their moisture and releasing it, tend to top out at about 30,000 feet, 40,000 feet. But when that does happen, then you create a thunderstorm situation. And when that moist air is carried up so high, these are the conditions when it would rain. So the incidence of rain depends on whether the temperature profile of the atmosphere happens to be like this or like this. That changes from a day-to-day basis, but we can measure it with a balloon. Just take a balloon with a little radio transmitter and a thermometer and release it in the atmosphere and measure the temperature profile. And what that means is that we can tell at what level cloud would start to form. We can also tell whether a parcel of air from the ground, because we know what the ground conditions are, whether it would actually reach that level. So we can tell whether cloud would actually form, and we can also tell how high that cloud would develop. And we can also forecast through the day as the ground temperature changes. We can basically forecast whether there's likely to be thunderstorms. We can't tell exactly where those thunderstorms are going to be, but we can tell whether a cloud, once it starts to form, is just going to bubble around, become a little cumulus cloud, or whether it's going to accelerate into a cumulonimbus thunderstorm cloud. And the relative probability of that determines, more or less, what the average rainfall is. That determines what kind of lifestyle humans would have. It determines the vegetation, it determines the fauna as well, and determines what kind of crops could be grown. And long term, it determines the climate. So all of this is dependent on this little bit of physics as to buoyancy and also the temperature profile of the atmosphere. And that depends on cloud cover and sun and what the nature of that terrain or sea might be. And all of this is in fine balance. So our survival really depends on understanding this.